So now we move to Alexander Dolgo from Conundrum, talking about Conundrum Euler, a AI defects detection system. So the stage is yours.
Thank you. Can you hear me well? Cool. I'm still expecting my slides to appear. I think this is it.
Okay.
Perfect, yeah, thank you. So it's called the power of industrial intelligence, but I would call it full potentials of industrial intelligence. I'm Alexander, the CTO of Conundrum, which is still a small startup. We're still young, about 4 years old, and 80 people in total. More than half are data scientists, talented guys. And we are creating state-of-the-art artificial intelligence software for industrial optimization. I'm going to tell you about the quality control, as probably our competitors just did. But first of all, could I ask you who's familiar with quality control with AI? Maybe some hands here. Yeah, so few people are familiar. And what areas? Like if it's like piping, metal, steel? Yeah, cool. That's the easy thing. We faced a few issues with the FMCG production, and I want to tell you about the problems that we faced and how we overcame those, and what lessons have we learned. So we are now in a point which we are called Industry 4.0, and in our regular life we have everything smart, like smart watch, smart television. Now we have smart manufacturing here, which mostly means that everything is computerized and we have digitalized everything. And mostly it's artificial intelligence, more or less, like some easy model or deep learning. And this brings us big value, but for a big price. So for having a quality control, we have to have a data set. We have it properly, carefully labeled, probably manually, if there's no any tricks applied. We have to retrain the model, which could cause the big time consuming. And any tiny change in the pipeline could bring us to big, great performance degradation of the model. So we ended up created Euler for quality inspection. When we train and scale the model way faster than the regular way, maintained an even the better level of performance. We created this with a 3D model. Just a second. Yeah. So we could create a 3D model to train the pipeline, and only near ideal samples needed to fulfill the pipeline. But before I continue diving into Euler, let's start from some history and evolution of the quality control. So the classical approach is regular pixel by pixel comparison. So we just take one ideal sample and one defected sample, put each one onto another, and get the difference pixel by pixel. When the image is black, there's no difference in the pixel, and when the image is highlighted, there's a defect, probably. So the main disadvantage of this, it just doesn't work in real life. So we always have objects laying on the conveyor belt with different position. They even can intersect each other. It could be different textures on the background, different textures on the foreground, on the objects. It could have some lighting problems, different reflections, and so on. And it's impossible to apply the pixel by pixel difference, especially if it comes to new production items when there's no defect and no production item, produced items even existed before the training of the model. So here we come to the simulation. So we get the simulated object, and we mix the object which we simulate with the real one. And then the first step, we generate the defects based on the physics. If you familiar or have heard about ANSYS or SolidWorks, you probably could recognize the image and how physical defects are generated. But at this point, we are still on the page of the history when we have it's mostly a 3D, right? So it's probably almost impossible to train the model properly. This way, we have applied style transfer for the image. And if you see the animation, the difference disappears on your eyes. So naked eye of the human cannot recognize the difference between the simulated object and the real one. Neither the model can. It applies texture, shadows, reflections, and all that kind of textures and noise to emulate the real images. So the model cannot recognize the difference and can be trained this way. And the last step is the segmentation of the data set. But the good news is, as soon as the data set is generated, the label is generated as well, and we don't need to label the data. After all, we have a quality assurance that can recognize the defects up to 0.1 millimeters, and basically it's limited only the camera resolution. And also, what's more important, we could divide the defects by segments by type of the defects and severity, because the small defect has more severity than the bigger one in some areas. So what we've learned so far, but that's basically the common thing for CV. We still need to maintain the quality of the picture, right? We still have to maintain the quality of the camera, the image, and the environment. But on this cost, we have a pipeline which allows us to recognize the defects with different positions under the objective, the lens, and different kind of defects and multiple defects under the single shot. That's cost reduction we come up with our clients with. That was caused because they on FMCG production, fast-moving consumer goods, they cannot apply the usual approach, and they applied our Euler system, and they got up to 75% cost reduction on the quality assurance after the manual control that they had before. That's it. Thank you. And I think I'm out of the time. So if you have any questions, please reach me out. I'm here with the label Conundrum on my hoodie. Please, I'm here for your disposal.
Thank you, Alexander from Conundrum. Even if you run a bit late, I could allow one question if there's one from the jury members, for the sake of fairness. So, Olaf.
Thank you for the presentation. Can you explain very briefly what is the USP? What is the essence of what you offer here? And how does it differentiate from other, say, AI approaches?
Yeah, could I see my slides here?
No,
no?
Slides are
okay.
gone, sorry.
So we basically created the full pipeline from training from creating the data set, training the model, and applying the model in an inference. And there's two basically innovative steps here. First is generating and labeling the data set on the 3D model with the style transferring, and then the pipeline of the training of the model. So for FMCG, let's say you have a toothbrush and you had it like blue, and you need to produce new item like green one. You need to train the model with a new item, and you have no data set before you created the item. We allow that to happen.
Okay, thank you, Alexander from Conundrum.
Welcome.